Okay, so this is lesson 3-2, and we're looking at the difference between mass and weight. And these terms are oftentimes confused, and so I want to make sure that you understand and you're able to differentiate between the two terms. So we're going to just kind of make a little T-chart here. We're going to have mass over here, and we're going to have weight over here. So let's talk about some differences between mass and weight. First of all, what is mass? Mass is the amount of matter or the amount of stuff something has, an object has. It is measured in kilograms, and it is independent of location. So what does that mean? If I take 1 kilogram and I put it on the moon, it's going to be 1 kilogram. If I take 1 kilogram and I put it on Mars, it's going to be 1 kilogram. The amount of matter is not going to change. So 1 kilogram on the moon is 1 kilogram on Earth, Mars, Jupiter, whatever, okay? It's the amount of matter, and that's not going to change just because of location. Okay, so now let's talk about weight. Weight is the gravitational pull or force on that mass or object. Okay, it's the gravitational pull on that mass or that object. And it has to do with all masses attract all other masses. And the big mass around, obviously, is the Earth. So if I draw here the Earth, and then here you are standing on the Earth, right? You and the Earth are attracted to each other gravitationally. Weight is that gravitational pull of the Earth on your body or on some object. It is measured in newtons, and it depends on mass and location. I mean, we all know that something that has more matter or has more mass, it weighs more, right? But it also depends on location. So if I were to take 1 kilogram on the Earth, 1 kilogram has a weight of 9.8 newtons. On the moon, 1 kilogram has a weight, I want to say it's 1.6 newtons. So the weight of that 1 kilogram is going to depend on the gravitational pull. And since the moon is smaller, there's going to be a smaller gravitational pull. Sometimes we refer to this as the gravitational field, or you know it as the acceleration due to gravity. So sometimes this is also called the gravitational field. Okay, so let's look at a problem. But here's the equation. So Fg, and this is a little subscript here, the gravitational force or the weight. Normally we say gravitational force, the vector, whereas weight is a scalar quantity measured in newtons, is equal to the mass of the object and multiplied by the gravitational field or the acceleration due to gravity wherever it's located. Okay? So right now we're going to be on Earth, okay? So a student weighs 120 pounds. That's how we normally think of weight, in pounds, but that's the English system. And everything in physics, we use the metric or the international system, the SI system. So the first thing we need to do to determine the student's mass in kilograms, we need to convert, because this equation up here, all right, that equation, this force, this gravitational force of this weight is measured in newtons. So I'm going to take 120 pounds, and I'm just going to use dimensional analysis, and I'm going to convert. And the conversion factor here is 1 pound is 4.448 newtons. So what I can do, take out my calculator, 120 pounds times 4.448. This student weighs 534 newtons. Okay, that student weighs 534 newtons. Now that would be this gravitational force, or this weight. That equals m, the mass, times g. Well, for Earth, we know g is 9.8 meters per second squared. So then if I take that 534 newtons and divide it by 9.8, this person has a mass of 54.5 kilograms. And that's going to be its mass everywhere, on the moon, on Earth, Jupiter, Mars, Pluto, whatever. That's its mass everywhere. Okay, notice I'm not using negative 9.8 here because we're talking about weight, which remember is a scalar quantity. So really I just need to know the magnitude of the acceleration due to gravity. Now it says determine your weight in newtons and in pounds on the Earth. So we have this student, okay, that has a mass. So again, we're using our equation, Fg, and this is a little subscript, equals mg, okay? We're looking for Fg. We know the mass, even on the moon, for that student is 54.5 kilograms, but the acceleration due to gravity on the moon is 1.6 meters per second squared. And that's also known as the gravitational field. So now if I take that mass and I multiply it by 1.6, this student is going to weigh 87.1 newtons on the moon. So you can see that on the moon, the student's weight is much different than its weight on the Earth, because the weight depends on location. Now, if I were to take that 87.1 newtons, I can now convert it back to pounds because, face it, that's how we think. We think in pounds. So I'm going to take the conversion factor, 4.448 newtons equals 1 pound, to convert this back. So if I take the 87.1 and divide that by the 4.448, that would be, let me make sure I did that right, 87.1 divided by 4.448, that is around 19.6 pounds. Okay, so here, this equation, we use this a lot. Fg equals mg. Fg is the weight, or the gravitational force, in newtons. M is the mass in kilograms, and g is the acceleration due to gravity, or the gravitational field, for whatever location, Earth, Moon, Mars, whatever. Okay, I do want to point out, if we have a person, let's say this is the Earth, and we have a person standing on the Earth, if we were to draw a free body diagram for that person, we know that there's this downward gravitational force, and that's because of the gravitational force between that person, that mass, and the Earth. So most of the time we will label that gravitational force Fg, but sometimes you will see let's label this as mg. Okay, so just remember that mg is the weight or the gravitational force. It's always going to point down towards the center of the planet.